Hey friends, it's Ben again. This is a video for the differential calculus class. We are taking a look at using the quotient rule. Okay, so the quotient rule, as you might guess, is taking a derivative where you have two things being divided. Uh, we don't have a lot of other rules set in place just yet, so you may find that the examples that we're looking at are the same thing over and over again, just with minor tweaks here and there. So hopefully it won't be too terribly boring, but let's take a look at some examples doing this. All right. Go. So the thing that you have to keep in mind here is our quotient rule. I'm going to put this out to the side. If you have f over g prime, you'll have f prime g minus f g prime, the whole thing over g squared. Okay? So if we're doing that for this thing here, then we have to take the derivative of the top, and the top is this 1 minus x squared. The derivative then is minus 2x times this 1 plus x squared minus, now you leave the 1 minus x squared alone, and then you take the derivative of the bottom, which is a plus 2x. And we're going to divide all that by the 1 plus x squared squared. We need to simplify it because of the fact that we're going to use it here to figure out where the tangents to the graph are going to be horizontal. So I'll distribute out to get minus 2x cubed, and then minus another 2x and plus 2x cubed, all that divided by quantity 1 plus x squared squared. Something to bear in mind with this is that you will never benefit by expanding out the square in the denominator. Okay, so never multiply out those denominators, leave them as they are. What can I cancel here? Looks like the 2x cubes go out, and then I have a minus 4x on that. So I'll have minus 4x divided by the 1 plus x squared squared. Now the question asked us, where are the tangents horizontal? That would be where the slope of the tangent is 0, or the derivative is equal to 0. If you have a fraction that is set equal to 0, the only way that can be satisfied is if the numerator is 0. So we have here to deal with minus 4x equals 0, which says that you are dealing with x equals 0. If we look at the point we want to talk about, an x value of 0, we would plug that back into the original function and get out a 1. So the point 0, 1 on the graph is going to be where the tangent line is horizontal. And so I don't have a graph of that here to show you real quick, but yeah. All right, so this other example here asks us to find another derivative using the quotient rule, and this time we've got an e to the x. Again, we're going to ask the question, where are the tangent lines horizontal at? So a similar kind of problem. So we're going to calculate q prime of x, and we just have to remember, take the derivative of the top first. Derivative of e to the x is always easy because it's always the same. Derivative of e to the x is e to the x, and then times the bottom minus, now we'll leave the e to the x alone, and the derivative of the bottom was 1. And now we have our bottom of x plus 1 squared there. So if you simplify that, let's see, we might want to expand first and get e to the x times x plus e to the x minus e to the x all over the x plus 1, the quantity squared, quantity squared, and you spot the e to the x's are going to cancel there, and so we end up with this being x e to the x divided by the quantity x plus 1 squared. Now, again, we're asking the question, where are the tangent lines horizontal? So we set it equal to 0. Denominators can never make it be equal to 0. They can make it approach 0, but, you know, not equal to 0. That tells us that we need x e to the x equal to 0, but e to the x is never equal to 0. So that tells us that our x is 0. And then if we plug that back in to the function, we would say the x is 0 and the y is, let's see, e to the 0 is 1 divided by 0 plus 1, so 0, 1 is where our tangent line turns out to be horizontal. Okay? All right. So here's another one, and this time we're asked to find a tangent line for the function. So the tricky bit is to remember that the square root of x, is really x to the 1/2 power, okay? So r prime of x, we'll take the derivative of the top first, and that's just 2 times the 1 plus the square root of x, okay? And then minus 2x minus 1, and the derivative of 1 is 0, but the derivative of x to the 1/2 is 1/2 x to the minus 1/2. So I should have drawn my bar a little further out there. In the denominator, we'll have 1 plus square root of x, or if you like, x to the 1/2, quantity squared. Please remember you cannot distribute the square across there. So that is not going to be equal to 1 plus x. It'll just be 1 plus the square root of x quantity squared. And there is no benefit of expanding that denominator. Okay? All right, I'm going to simplify that top where I can, and I'll have a 2 plus 2 square roots of x minus, oh gosh, 2x times 1/2. X to the minus 1/2 would be really 1 over the square root of x, and then plus 1/2 this 1 over the square root of x. So that looks pretty messy. I'm going to have a 1 plus the square root of x squared, and now I'm going to see what I can do here. 2 plus 2 square roots of x, and let's see, those cancel there. X divided by the square root of x means I would have a minus square root of x, and then plus 1 over 2 square roots of x. All that divided by 1 plus the square root of x squared. Well, I can get a little bit of mileage out here. This minus square root of x will combine with that. And so now this would end up being 2 plus the square root of x plus 1 over 2 square roots of x. If you don't like the way that looks, then you could multiply the top and bottom by the square root of x and have 2 square roots of x plus 1/2 whole divided by 1 plus the square root of x squared times the square root of x, I guess. If you want to multiply by 2 in the top and bottom, even better, but I don't think it really looks any better. Okay, so I would be perfectly happy with this answer right here. But if you want to, you can fiddle around with it a little bit and get it into a form that you like a little better. All right. So next, we're going to try to figure out where this function is increasing and decreasing. So we'll have to start out with our quotient rule here. S prime of x equals, and we take the derivative of the top first, so that gets us 2x, and then e to the x here, and then minus, now we'll leave the x squared alone, and derivative of e to the x is e to the x, and then on the bottom you have to square e to the x, which is really writing e to the 2x, okay? Now, if we want to figure out where it's increasing or decreasing, we're going to have to, you guessed it, find out where it's 0. So we want to factor out an e to the x from the top, and it looks like we can also factor out an x, and then a 2 minus x, okay? All that divided by e to the 2x, but conveniently, since you've got an e to the x as a factor, and e to the 2x there, then that says you'll have an e to the x down there. For our purposes, it doesn't really do that much, but it does make it a little simpler when we do calculations with it. We need to set that equal to 0, and that says that x, 2 minus x equals 0, because only numerators make things 0. So either at x equals 0 or x equals positive 2, those are the only places where it's going to be able to change sign. So we line this out. 0 and 2 are our change points. Our sample points, we can go at -1, at +1, at +3, okay? And so if we calculate out here to the side, s prime of, I started to say x, but s prime of -1, s prime of +1, and s prime of 3. Since the function can only, the derivative can only change signs at those values, or at the values of 0 and 2, whatever it takes on at -1 is what is the sign that it takes on for all x values less than 0. And at 1, the sign will be the same as what it is for all values between 0 and 2. And at 3 for all values greater than 2, okay? So then we're doing a quick calculation there. -1, if you plug that in on the top, you would have, let's see, -1 times 2 minus a -1, so -3 divided by e to the -1, which is negative. When you plug in +1, you'll end up with 1 over e to the 1, which is positive. And when you plug in 3, you'll end up with -1 divided by e to the 3, which is negative. So if we write down where it is going to be increasing and where it's going to be decreasing, for increasing, we choose where it's positive. And that means our sample point of +1, which was in this interval from 0 to 2. So for increasing, we will just get the interval from 0 to 2. For decreasing, we got negative derivatives on the other two spots. So that means from -infinity up to 0, it was decreasing. And then it was decreasing again from, what was it, 2 to infinity. And then you write a u between those to indicate that you want the values from both intervals. Okay? So, I don't like how that turned out. Oh well. All right, I think that's, oh, no, I've got one more example here. All right, so the one more example is because we've got an example like this in your assignment where you're asked to show that y equals some function is a solution to a differential equation. Everybody always thinks that those problems are super duper hard, but they are in fact meant to be super duper easy, okay? The notion is if you're asked to show that some function here satisfies some equation here, then you figure out what the left-hand side of the equation is, and you figure out what the right-hand side of the equation is, and you show that they're equal. So we can do that here, and we'll find y prime, of course, is going to require us to use a quotient rule, right? So we will do 1 times e to the x, and then minus x times e to the x, because the derivative of e to the x is just e to the x. So that makes that easy. Then this e to the x squared will be e to the 2x. And then you can see that an e to the x will factor out there. And you have e to the x times 1 minus x, and then e to the 2x. Then cancel out one of those, and you end up with 1 minus x divided by e to the x. Okay, now we're going to show that the other side is the same thing. So we're going to take y over x minus y. And so that means that you have to plug in x over e to the x on each one of those where the y is. And so on the first piece there, you'll be able to simplify it as x over x e to the x. And that has some cancellation happen. So then this turns into 1 over e to the x minus x over e to the x. And since they've got the same denominator, you can turn it into 1 minus x over e to the x. Since these two things here are the same, we have shown that this y over y, or y prime equals y over x minus y is true for y equals x over e to the x. Okay. Oftentimes with it, the algebra gets a little messier than that. But when you're asked to verify you have a solution to a differential equation, all it really means is show that the left-hand side and the right-hand side are both calculations that end up getting you the same thing. You don't have to solve those equations, you just have to show you have an equation. Wouldn't that be nice? You know, when you're solving a differential equation, if it said to you, just show this is a solution, you just stick the number in. Here it's harder because the variable is a function. So you have to do something with it. So, but that is kind of a prelude to the study of differential equations, which is something that comes after calculus, and it's super duper instrumental in everything about physics and engineering and every one of the STEM disciplines. So, all right, I'll let you go with that, and I will see you in class.